Chapter 5 Helmholtz energy and Gibbs energy. Section 5.2 U, H, A, and G depend on P, V, T, S. In thermodynamics, there are many thermodynamic functions. Among those, U, H, G, and A are very important. They denote the internal energy, enthalpy, Gibbs energy, and Helmholtz energy of the system. U, H, G, and A depend on pressure, volume, temperature, and entropy. P, V, T, S. And we have equations that connect U, H, A, and G. U is A plus Ts, H is U plus PV, G is H minus Ts, and A is G minus PV. There are 4 other equations that connect U, H, G, and A. Among all these thermodynamic functions, only pressure and temperature are intensive properties that do not depend on the amount of the substance. U, H, G, A, V, and S are extensive properties that are proportional to the amount of the substance. The SI units for U, H, G, and A are all joules, and 1 joule is 1 kilogram meter squared over second squared. U, H, A, and G depend on PV and TS, and you can see all those equations over there. The SI units of PV, TS are Pascal for pressure, cubic meter for volume, Kelvin for temperature, finally joule per Kelvin for entropy. And also you can replace this joule with 1 kilogram meter squared over second squared. It's just a little bit too tedious. 1 Pascal is 1 Newton per square meter. Well, it's just remember pressure is force over area. And 1 Newton is 1 kilogram times meter over second squared. You can just memorize this by remembering force is equal to mass multiplied by acceleration. And also 1 Pascal can be written in terms of kilogram meter a second, because we can replace this Newton here with kilogram meter per second squared. And therefore 1 Pascal is 1 kilogram times meter to the power of -1 second to the power of -2. And also this can be written as 1 joule over cubic meter. Well, again, it's just because 1 Newton times 1 meter is a joule. So that's why. Now we have 1 Pascal multiplied by 1 cubic meter equals 1 joule. If we multiply P and V, the product PV has a unit of the unit of energy. Therefore, the SI unit of PV is joule. Same for TS. The product of temperature and entropy should be in the unit of energy. And the SI unit of the product TS is also joule. Again, we need to memorize all these equations that connect the 4 thermodynamic functions U, H, A, and G. For a fixed amount of a pure substance, its internal energy U depends on PV, T, and S, not N, because if you have a fixed amount, N is constant. Out of pressure, volume, temperature, and entropy, only 2 are independent variables, and you can pick any 2. For example, you can view the internal energy as a function of PV. And you can write du is delta U over delta P times dP plus delta U over delta V times dV. This is correct, but not very useful in thermodynamics, because this partial derivatives do not really have a clear physical meaning. Also, we can write U is a function of Pt. Similarly, du is delta U over delta P times dP plus delta U over delta T times dt. And pay attention to the subscripts. This equation is also correct, but not very useful. The reason is, yes, u is a function of two independent variables. What about the two other variables? The two other variables depend on the two independent variables of your choice. But if you choose PV as the independent variables or PT as the independent variables, the equations you get are correct, but not very useful. Very often we write U as a function of temperature and volume. Sometimes we write U as a function of entropy and volume. If we select temperature and volume as the independent variables for the internal energy, and we can write du is delta V over delta U over delta V times dV plus delta U over delta T times dt. And this term, delta U over delta V on a constant temperature, we can later prove this to be T times delta P over delta T minus P. And this can be easily measured. And also it can be derived for different substances. That's why it's convenient. What about delta U over delta T on a constant volume condition? On a constant volume condition, work is 0, so delta U is just delta Q. Delta Q over delta T is just C. So that's why we have C sub V here. Again, this is convenient when we view U as a function of temperature and volume, because we have something with physical meaning, easily measurable in front of dV, and this C sub V is also easily measurable, and it can be determined for the substance fairly easily, and then we can study how U depends on B and T. Actually, we can express U as a function of entropy and volume as well. This is because du is dq plus dw. For a reversible process, du is dq reversible plus dw reversible. And remember, the definition of entropy in thermodynamics is indirect. Its ds is equal to dq reversible over T. Therefore, dq reversible is TdS. What about dw reversible? It's simply negative p external dV, and since it's reversible, p external can be replaced by p. So now du is just TdS minus pdV. This is a really simple expression, and it contains PV, T, and S. When do we use the first equation, U as a function of TV, or the second equation, U as a function of entropy and V? Really depends on which of these equations is more convenient to use under the specific conditions. Later you will see. We will use this equation and this equation in many derivations and numerical calculations. And because du is equal to TdS minus pdV, and also we have the definition of H, A, and G. H is U plus PV, A is U minus TS, G is H minus TS. We can do some simple derivations here. DH is just du plus PV, which is simply TdS minus pdV. This part is du, this part is dPV, and we cancel negative pdV and positive pdV. DH is TdS plus VdP. dA is du minus dTs. This part is du, TdS minus pdV is du, and then minus TdS minus SDT. Therefore, dA is negative SDT minus pdV. And also we have this dg over here. dg is dH minus TS. dH is TdS plus VdP right here. And we can expand TdS using the product rule in calculus. And finally, dg is negative SDT plus VdP. U, H, A, and G all depend on PVTS. For a fixed amount of a pure substance, only 2 out of these 4 variables, PVTS, may be chosen to be the independent variables. You can choose any 2, but sometimes it's just more convenient to choose, for example, if you have G, if you look at G, It's probably better to express G as a function of temperature and pressure. It's just more convenient. And you know how G depends on temperature. It's just negative entropy. And you know how G depends on pressure. It's just volume. So it's just convenient. So in summary, we have these four exact differentials. It can tell you it's often more convenient to write U as a function of S and V, H as a function of S and P, A as a function of TV, and G as a function of TP. In addition, we use these two equations for U and H. It's also very convenient to express U as a function of Vt and H as a function of Pt. Again, one reason is it's easy to measure the change of temperature, volume, and pressure. There's another reason. Delta U over delta V on the constant temperature can be expressed in this form. And you look at this, it involves only pressure, temperature, and volume. All three quantities can be easily measured. Delta H over delta P is V minus T times delta V over delta T on a constant pressure condition. Again, this can be measured experimentally easily, and it can be derived for other substances as well. So it's just convenient to use these expressions for du and dH as well. Now, what about this delta U over delta T on a constant volume condition? It's just isochloric heat capacity. Delta H over delta T under constant baric condition is just the isobaric heat capacity. So again, it's just that we choose the independent variables depending on whether it's convenient for us to use to achieve our goals in the calculations or derivations.